Welcome to Monday Morning Methane. Excited to talk today about a few of the challenges facing measurement informed inventories. Okay, so big week for many of you today, big week for Highwood as well. This is the week that we all put our heads down and finish our OGMP 2.0 reports, which are due Saturday for the year, for the 2024 reporting year. So good luck to everyone working on those, and good luck to the Highwood team. We've got our hands full. This week, in light of OGMP 2.0, I wanted to talk a little bit about measurement informed inventories. We've been building out a lot of level 5 inventories, combining measurement data from a broad range of sources. So I wanted to look at a little bit of that measurement data and talk about some of the challenges that we have in taking that measurement data and putting it into inventories. And to illustrate that, I wanted to look at this plot, which I really like, from Coleman Volrath and Chris Hugenholtz and their team, my former lab at the University of Calgary. They put this out in a recent paper. And the reason I like this figure is that it really illustrates how using different technologies for measurement can often lead to different results. And so the first caveat I want to say is that this plot is not intended for an apples to apples comparison. It's just an illustration of how different technologies deployed in different circumstances can lead to different measurement outcomes. So before I jump into it, I just wanted to explain a little bit how these plots work if you've never seen one of them before. And I'm going to do it using the series of gray dots. And so each one of these series of dots in this plot, each one of these lines represents a study, represents a series of measurements. And you can see in the legend that, for example, this gray line, series of gray dots, is an OGI, optical gas imaging camera survey, and high flow sampler survey in British Columbia, Canada. Each one of these dots represents an individual measurement in that survey, and you can see the corresponding emission rate for each one of those dots if you look at the x-axis. One really interesting thing to note here is that this x-axis spans 10 orders of magnitude. This is an absolutely massive variation in the emission rates that we see, even from within individual campaigns for individual technologies and regions, but especially across campaigns. Now, the way that you interpret the y-axis in this graph is that the very top dot, these dots are ranked according to their emission rate. Obviously, that's why they make a line going from left and right. And the very top dot represents the emission rate that 100% of sources are below that rate. So if you look again at this gray line, the OGI high flow sampler study, 100% of sources, if you go over to the one, the cumulative proportion, are below 10 to the 0 or 1 kilogram per hour. If you look for this one over here, if you go to the other extreme, I don't even know what color that is, kind of a blue-gray. This is Tropomi satellite data. 100% of sources in this study are above 10 to the 5 kilograms per hour. And so one of the first really interesting things I wanted to illustrate in this figure is, even though these aren't apples to apples comparisons, there are some trends that emerge. And this isn't in the paper. This is my own analysis and interpretation on top. But if you start to break down what these lines are, there's a really interesting pattern here where the three lines furthest to the left with the lowest emission rates are all handheld measurement technologies. The next two lines are all vehicle-based measurement technologies. The next are aerial LiDAR, specifically Bridger, the leader in that space. The next two are hyperspectral imaging cameras, also mounted to planes. And then the top three with the highest emission rates are all satellites. Now, if you look at these, one of the first things you should notice is that there's not a lot of overlap between the categories. And this is strange. Shouldn't these different measurement technologies be measuring the same emission sources? Well, not necessarily. And we'll look at that in two different ways. The first is by looking at the bottom of these curves. Now, this is something that really makes sense. If you look at the bottom of the curve, and I mean, let's just choose one just for fun here. let's choose this orange satellite line. The bottom of the curve represents the smallest emission rate that was detected by that technology. And so for this orange line, which is Sentinel-2, the smallest one was around 10 kilograms per hour, actually very, very small for satellite, uncharacteristically small. And so what that number represents is effectively the minimum detection limit. We like to speak in terms of probability of detection because there's only one in this study. It's a very, very low probability that source was even detected. But the limiting factor on the dot at the lowest end of these curves is typically a combination of technology performance and environmental conditions at the time of measurement. And so it makes sense that handheld technologies, where you're really, really close to the source, in some cases centimeters away, you're going to find much smaller emission sources. And for satellites, which are in many cases orbiting, in low Earth orbit, 500, 600 kilometers away from the Earth, you're not going to be able to find those same small sources. And so the smallest dot that you get is going to be quite a lot bigger. And the way I generally like to explain this, it's kind of like human senses: sight, smell, anything that if you're closer to something, you're way more likely to detect it. And if you're farther away, it's just physically more difficult to do so. So that's intuitive, right? The second part about this that isn't intuitive, which makes building measurement informed inventory so difficult, is the top and the top of these curves. So let's look at this gray handheld study again in British Columbia. Presumably, there shouldn't be anything limiting the highest emission rate that these technologies. You never hear anyone talking about upper detection threshold, right? I mean, it is technically a thing, but it's not something that we spend a lot of time talking about. And these cameras should be able to detect the sizes that you see in some of these satellite campaigns, but there's really just no overlap. And so the largest emission rate we see with handheld, if you go down, if you draw a line straight down from that dot, is about the middle of what we're seeing for a truck. If you go up for the trucks and you draw a line down from the trucks it's about the middle of what we see from aerial LiDAR. If you go up on LiDAR and draw a line down, it's about the middle average value of what we see from hyperspectral planes. And if you go up to the highest sources for planes and you draw a line down, it's about the average value, and I'm really kind of hand waving here, but about the average value that you would see for satellites. Now, why is this? I hope we can have a good debate in the comments. I have really good ideas, but I just wanted to put that in front of you. I think there's a number of things that could be going on here, but this is really important because there are very large, very rare events that occur, and incorporating them into measurement informed inventories is very, very difficult, and especially incorporating the ones that you didn't detect because they are so rare and we know that they happened is very challenging as well. We do a lot of work on this at Highwood. Happy to have conversations about it anytime, but look forward to hearing your thoughts in the comments. Thank you for joining today on Monday Morning Methane. Hope everybody has a wonderful week.